Good morning, students. This is first lecture on chapter 2. So if you remember last time, in the last lecture, we discussed about systems of units, right? So that was chapter 1 of your book, and today we are starting with chapter 2. So just a flashback, just to review what we did last time. We talked about systems of units. So basically we have two systems of units, the System International or SI system and US system, right? So we have different units for both the systems for this to measure or to represent physical quantities, right? So then we did some problems, and then you have a homework on chapter 1. So please do the homework so that you have enough practice on the system of units and how to convert from one system to the other system. So that was the last lecture. Now today we are starting with chapter 2. Now what is chapter 2? Chapter 2, the topic is force vectors, vector operations, and vector addition. Okay, so this is the topic for this part of the lecture. So what are we going to discuss? We're going to discuss about force vectors. As you remember that niche in the introduction, we talked about mechanics and statics, right? So once we talk about statics, right, we talk about forces. Forces acting on the bodies, acting on the structures, acting on different members, right? So what is a force? Is it a scalar or a vector? You know that force is a vector, right? Because force has some magnitude and some direction. Okay, so first of all, we need to understand the difference between scalars and vectors. You must have gone through this concept in your physics course, so you all must be familiar of the scalars and vectors, right? So scalar just has a magnitude, just a number, right? Without any direction. Maybe the mass of a table, right? Maybe it's 2,000 kilogram, right? So that's just a number, 2,000, with no direction. So that's a scalar. On the other hand, if there's a force, let's say 100-pound force is applied on that table, right? So that force is a vector quantity. Why it's a vector quantity? Because it has a magnitude, let's say 100 pounds, and a direction, right? At some angle to the x-axis or y-axis or z-axis or in some direction, right? So we know that force is a vector. Similarly, if you talk about velocity, velocity is a vector, right? It has a magnitude and some direction, right? So that is the difference between scalars and vectors. So in this topic, we are going to talk about force vectors, vector operations, vector addition, right? How to resolve a two-dimensional vector into its components, or how to add two-dimensional vectors using Cartesian vector notations. Okay, so in this picture, you can see that, let's say if this is a pole, right? We have x-axis here, we have y-axis here, right? This is the coordinate axis in 2 dimensions. We already know about it. So if there are 3 forces acting on this pole, right, at this point, so we have F1, we have F2, we have F3. Now, what is the purpose of doing this, all this mechanics, right? The purpose of doing this mechanics is that we want to make sure that a structure or a body is safe for the applied loads. Like on this pole, we have these 3 forces applied on this pole, right? At this point, let's say point A. So at point A, we have 3 forces which are being applied, right? Let's say they have different magnitudes. Let's say 100 pounds, 200 pounds, 500 pounds, something. Let's not go into details of the magnitudes, right? But again, let's come back to the purpose of doing this, learning this concept and doing this mechanics stuff, right? So what is the purpose? The purpose is either this pole is safe for this loading, or this is going to break. This is going to fail under this loading, right? So how can we do that? If we have these three forces, either we have to analyze these forces one by one, and then it's a long process, right? But on the other hand, if we can find a resultant force of all these three forces, let's say FR, right? Let's say here we can say that, okay, this one is FR, right? FR, which is a resultant force of F1, F2, and F3. So then we can just analyze this system with FR, the resultant force, and we can say, okay, this is this structure is safe, or this structure is not safe, right? Or it's going to fail. So that's the purpose of resolving a vector into its components or addition of vectors. Okay. All right, let's move forward. So same thing what we have discussed in the last slide. What is the application of vector addition? Let's say if this is a hook, right? You can see in this figure, there's a hook and there are three chains. These are the chains which are applying some forces on this hook, right? Let's say F1, F2, and F3. Three forces are being applied to this hook due to these chains, right? So now we need to decide if the hook will fail, bend, or break, or maybe it is safe, right? So that is the purpose of doing all this mechanics, all this statics, okay? So to do this, we need to know the resultant or total force acting on the hook as a result of these three chains or three forces, right? So again, that's the purpose, to get this FR, right? The resultant force, so that we can analyze the system. We can analyze this hook, either it is safe or it's going to fail. So that is the purpose of doing all this vector addition and vector resolution, right? So in this case, let's say we have this guy F1, we have this guy which is F2, and we get this which is F1 plus F2. So we add F1 and F2 and we get this which is the addition of F1 plus F2. Now if you add this guy and this guy F3, right, then we get this FR. We get this FR, this guy. So this is the resultant of all the three forces acting on this hook. So we can just do one analysis with FR instead of going for three analyses, first with F1, then with F2, then with F3. Long work, right? Lengthy work. So we don't need to go for that. We just do one analysis and we can make out either the system is safe or not. All right? Okay, so I hope by now we are clear about what is the purpose of doing all this and why do we do all this. Okay? All right. So as we discussed earlier in this lecture, today's lecture, the difference between scalars and vectors. So section 2.1 of your book, we have scalars, we have vectors, right? Scalar quantities, vector quantities. Again, scalar is just a number. Vector is a number with some direction, magnitude with some direction, right? What are the examples of scalars? Mass, volume, right? Length. All these are scalars. What are vector quantities? We have force, we have velocity, right? They have some magnitude and they have some direction. Okay, so that is the difference between scalars and vectors. Okay, and these are some of the examples of our scalars and vectors. Okay, all right. Characteristics of scalars and vectors, we already discussed. Scalar just has a magnitude. Vector, it has a magnitude and direction. Okay, so force has some magnitude and some direction, right? along x-axis, along negative x-axis, along y-axis, at 45 degrees, at 90 degrees, at 78 degrees, some direction, right? So that is your force, or maybe velocity. Okay, both of these are vector quantities. Okay, all right. So now let's talk about the addition rule. How do we add scalars? How do we add vectors? So for scalars, since we do not have any direction, we only have a magnitude, just a number. Just add that number, add the 2 numbers or 5 numbers or 10 numbers, right? And then you get the addition. Okay. So we can say simple arithmetic, right? Simple math. Okay. 2 plus 2, 4, 4 plus 5, 9, 9 plus 4, 13. So resultant is 13 because we don't have any direction, just a number. But if you talk about vectors, then it's a little different because it has magnitude and direction both. So we'll discuss parallelogram law. This is one method of adding the vectors, and then there's another method called as triangle method. They are sort of similar, but we'll study and we'll see. Okay. Now, how do we denote vectors and scalars? So for scalars, there's no special notation, right? But for vectors, we have bold font, a line, or an arrow, right? That's how you denote vectors. In your book, a vector quantity is represented like this guy, right? Bold, italic, and red. Okay, so you won't find arrows or a line on the vector quantities in your book, right? But it will be just bold, italic, and red. So that will show you that, okay, this is a vector quantity, right? And in our lecture slides, we'll have the same notation. We'll have the vector quantities in bold, red, and italic. Okay, so that was about scalars and vectors. I hope you got something out of this, scalars and vectors, and we know now what is a scalar and what is a vector and what is a difference between these two, right? Okay, now let's talk about vector addition using either the parallelogram law or triangle method. Okay, so let's talk about parallelogram law first. Okay, so here you can see we have two vectors, vector A and vector B. Now we need to add these two vectors, A and B, to get the resultant vector. So using this parallelogram law, how do we add A and B vectors, right? So just join them, join these two vectors, A and B, right? And then from this point, make a line parallel to vector B, right? So this is the line parallel to vector B. Now from vector B, the tip of vector B, draw a line parallel to vector A, okay? And these two lines meet here at this point P, right? Now from this start point, make a line to point P, right? Okay, this was your point P, okay? And this is your resultant vector, R, and R equals A plus B. And this is the parallelogram law, or this method to add the vectors, okay? So that's how you add 2 or more vectors with this method, okay? I hope we are clear with this. I mean, this is not something rocket science. This is just simple, plain method, right? Simple method. So you can just do some examples and make sure that you understand this parallelogram law. Okay. All right. Now let's talk about triangle method. It's almost the same as the parallelogram law, but just a little difference. Let's see. And always tip to tail. Tip is the arrowhead, tail is the tail, right? So again, we have these two vectors, vector A and vector B, right? Now let's draw vector A. So you draw vector A. This is your vector A, right? Now, tip to tail, okay? So this is the tip of vector A, right? This is the tip of vector A. So join or draw vector B from the tip of vector A, right? So draw vector B like this. So tip of vector A and tail of vector B join together, okay? So now you can join these 2 points in this fashion, and this is your resultant vector. This is your resultant vector of the addition of vector A and vector B. So R equals A plus B, okay? And you can do it in the other way also. You can do B plus A, right? And you'll get the same answer, right? So first you draw vector B. So this is your vector B. This is the tip. Now from this tip, draw vector A. So this is your vector A, right? So this is vector A, this is vector B. Now join these 2 points, and this is your vector R. Okay, so this is your vector R, which is the resultant of these 2 vectors, B plus A or A plus B. Okay, so these are the 2 methods which we use for vector addition, either the parallelogram law or the triangle method. Okay, all right. Now let's move forward and let's talk about a resolution of a vector. So we just talked about the addition of vectors. Now we are talking about resolution of a vector. So if we have a vector, how do we resolve it into its components? Okay, so resolution of a vector is breaking up a vector into components, right? Why do we need components? For vector addition, right? Without that, geographical method, right? Okay, so let's see how do we resolve a vector into its components. Okay, so in this figure A, you can see that this is u-axis and this is v-axis, right? This is your v-axis. Okay, all right, so this is u-axis, this is v-axis, and this is your vector f shown in blue color. Okay, now we need to find the components of vector f along u-axis and v-axis. So we call it f sub u and f sub v, right? So how we do that? Now, if you look at this figure B, what are we doing here, right? So this was your vector f. This is your vector f. Now, draw a line parallel to u-axis and parallel to v-axis from the tip of vector f, right? So you draw this line here, you draw this line here, right? And this is your f sub u and this is your f sub v. So these are the 2 components of vector f. So that's how we resolve this vector f into 2 components, f sub u and f sub v. Okay, and we can show it in this figure C, just as a triangle, right? So it's same like triangle method or parallelogram method. Okay, so this is your vector f, this is your f sub u and f sub v, the 2 components of vector f, right? And f sub u plus f sub v equals f, right? So it's kind of like using the parallelogram law in reverse. So same method which we did for vector addition, we can use to resolve a force vector. Okay, all right. So let's move forward. Now, addition of a system of coplanar forces. This is section 2.4 of your book. Let's talk about it. Okay, so we resolve vectors into components using x and y axis coordinate system. All right, so that last slide we discussed about u axis and v axis, right? But normally we use this x, y, z coordinate system. So since here we are talking about two-dimensional space, 2D space, so we only have x-axis and y-axis. They are always at 90 degrees, right? So this is your x-axis, this is your y-axis, okay? This is your force F, okay? Force vector F. Now, how do we resolve this force F into two components? Right, so along x-axis we have F sub x, this guy, right? And along y-axis we have F sub y, the y component of this vector F. Okay. Now another important thing, you must have already seen that in physics course, we have these unit vectors or direction vectors, I and j, right? And if we have 3D space, then we have k also. Right? So I, the vector I, which is a unit vector or direction vector, always acts along x-axis. And the unit vector or direction vector j is along the y-axis, or for the y-axis. So we use this and we call this Cartesian vector notation, right? Cartesian notation or Cartesian form. Okay. All right. So each component of the vector is shown as a magnitude and a direction. We already know that each component of a vector is also a vector. So that's why it has a magnitude and direction, both. Okay. All right. The directions are based on x and y axis because we are resolving the force vector according to x and y axis, right? Or we are using x and y coordinate system. We use the unit vectors I and j to designate the x and y axis. We already discussed about that, right? I, j, and k system in 3D space and in 2D space, we have I and j. All right. Okay. Let's move forward. So this is the same thing, right? This is the same thing. Again, we have x-axis, we have y-axis, we have this force vector F, right? Now we can resolve this force vector F into its two components, x component and y component. X component is F sub x, y component is F sub y, right? And we have these unit vectors I and j to show the direction of x axis and y axis, right? So how do we write it? How do we write this resolution of force vector F, right? So we write it in this fashion. F equals fx times I plus fy times j, right? So F is the original vector, fx is the x component, fy is the y component, this vector I is the direction vector showing the direction of x-axis, and this direction vector or unit vector j shows the direction of y-axis. Okay, and again, if you look here, this F is bold, italic, and red, right? The same notation as per your book. So this is a vector. Again, this I and j, you can see that they are also bold, italic, and red. So whenever there is a bold, italic, and red, just we can say that there's a vector quantity according to this book. Okay. Different books have different methods, right? So some books uses the notation of an arrow, right? So they write, let's say they write F and they put an arrow here. So that is the notation for vector quantity. Some books uses just a line, right? So line over the alphabet over the letter shows that it's a vector quantity. Anyway, so we are going according to this book. So we'll use italic, bold, and red for vector quantities according to this book. Okay. X and Y axes are always perpendicular to each other. We already know that, right? We know that X, Y, and Z axes are in 3D space, and in 2D space we have X and Y axes, and X and Y are perpendicular to each other. Okay. All right. So that's how we resolve a force vector F into its components, Fx and Fy. All right. Okay. Now let's talk about addition of several vectors. Right. So we have different vectors, maybe 5 vectors, 10 vectors, 20 vectors, maybe 2 vectors. Now we need to add all those vectors, right? How do we add all those vectors? Let's say again we are working in 2-dimensional space, 2D space. So we have x-axis and we have y-axis. Now we have, let's say in this case, we have 3 vectors. So we have F1, we have F3, we have F2. So we have these 3 vectors. Now we want to find out the resultant of these 3 vectors. So we cannot do that directly, right? Let's forget about the graphical method, right? So let's forget about the graphical method. Let's talk about this. How are we going to do according to the resolution of vectors? Okay. So what is the step 1? Step 1 is to resolve each force into its components, right? So we will resolve F1 into F1x, F1y. We'll resolve F2 into F2x, F2y, and similarly F3 into F3x and F3y, right? Let's do that. Let's do that first. Okay. Let's forget about step 2. So let's focus on step 1. Okay. So this was your F1. This was your F1. So now we'll resolve this F1 into F1x and F1y, right? So we have these 2 components, x and y components of F1. Okay. So this is a part of step 1. Okay. Now next, this is your F2, right? This is your F2. Okay. This guy. So now we'll resolve this F2 into F2x and F2y, right? F2x is the x component of F2, F2y is the y component of F2. Okay, so that is the resolution of F2 into 2 components. Now let's talk about F3. Okay, so this is your F3, this guy. Okay, now we'll resolve this F3 into 2 components, F3x and F3y. Again, x and y components. Okay, so after we are done with this step, let's go to the next step. Step 2. This is your step 2, is to add all the x components together, followed by adding all the y components together, right? So what are we doing here? We are adding all the x components and all the y components. So if you look at the figure, what are the x components? F1x, F2x, F3x. So we'll add all these 3, right, to find the resultant x component. And then we'll add up F1y, F2y, and F3y to find out the resultant y component, right? So that's what it says here. These 2 totals are the x and y components of the resultant vector, right? So FRX and FRY, let's say they are the x and y components of the resultant vector FR. Okay. All right. So now let's go to step 3, which is to find the magnitude and direction or the angle of the resultant vector FR. Okay. So we can do that in step 3, and to find the magnitude and direction of the resultant vector. Okay. All right. Let's move forward. An example of this process. So again, this is the same thing. We have x-axis, we have y-axis, right? Again, we are working in 2D space. We have three vectors, F1, F2, and F3. Different magnitudes, different directions, different angles. Okay? Now we need to add all these three, F1, F2, and F3. So instead of graphical method, we'll go for this method. We'll resolve these three vectors into their x and y components. Okay, and then we'll add up their x components to get the resultant x component, and then we'll add up the y components, all the y components, to get the resultant y component, right? So this is the same thing what we did in the last slide. F1x, F1y, F3x, F3y, F2y, F2x. So now we got the x and y components of all the three vectors. What next? So break the three vectors into components, which we already did in the second figure on the right, and then we add them, right? So how do we find the resultant FR, which is F1 plus F2 plus F3, right? So what is F1? F1 is F1x times I plus F1y times j, right? So this is your F1. This is your F2, and this is your F3, right? F1 has two components, x and y. F2 and F3 also have two components, x and y, right? But we also add here the I and j unit vectors, right? Because we are using the Cartesian notation, okay? All right, so now after doing this, now just make sure that you understand about this negative sign, and this negative sign, right? If you come back on this figure, so F1x, if you look at this F1x, this is positive x, right? So that's why we have a positive here, okay? F1y, positive y direction, so we have a positive. F2x, this guy is negative x direction, right? Negative x direction, so that's why we have this negative. F2y is positive y direction, so we have a positive. F3x, this guy, in positive x direction, so that's why we have a positive. F3y is in negative y direction, so that's why we have this negative, right? So that's how we use these positive and negative signs depending on the direction of these components. All right, so once we have this, then we can just add up all the x components and the y components, right? So F1x minus F2x plus F3x times I, right? Just take I as common. Then F1y plus F2y minus F3y. Keep the signs of the components, right? Times j. So this is your FRY, and this is your FRX. The resultant y component and resultant x component. All right. So what do you get? You get this form finally, which is FRXI plus FRY times j. Right? So in this system, or in this method, this I and j notation is compulsory, right? So we need to use this I and j notation, right? Because we are doing it in Cartesian notation, okay? And this is your Cartesian notation, I, j, and k, okay? So that's how you reached here up to FRX times I plus FRY times j. Now, what next? Next, you can find FR, the resultant vector, right? How do you find that? FR equals square root of FRX squared plus FRY squared, right? Because if this is your FR, this is your FRX, if this is your FRY, just use the hypotenuse rule and use this equation to find FR. And that is the resultant of all the three vectors which were shown previously, right? We had three vectors in the system, and now we have reached to one vector, which is FR, which is the resultant of all those three vectors. Okay. Now this vector FR is making some angle theta with the x-axis. How do you find that the angle theta with the x-axis, right? So we use this. Theta equals tangent inverse FRY over FRX, right? So that's how you get the direction of this resultant vector FR. Okay, so I hope you are clear with this example of using this method to find the resultant of two or more vectors, right? Maybe you have 10 vectors, 20 vectors, or maybe you have 2 vectors. You can use this method to find the resultant vector, right? Okay, let's move forward. All right, so let's do this example so that we are more clear on this method. So what is given here, let's say that this is a hook, right? And there are three forces. This is F1, this is F2, this is F3 in different directions, different magnitudes, right? F1 300 newtons, F2 450 newtons, F3 600 newtons, right? They have their own magnitude, their own directions. Now, three concurrent forces acting on a tent post. I hope you understand what are concurrent forces, right? Because all these three forces, F1, F2, and F3, are passing through this single point, right? So they're acting at one point. That's why we say that these are concurrent forces. Okay, so these concurrent forces are acting on this tent post, let's say a hook, and we need to determine the magnitude and angle of the resultant force. So we need to find FR. Now again, if you look back what we discussed, why do we need to find this resultant force, right? So what's the reason? We already talked about it, right? So why do we need to find this resultant force? Because we need to make sure that this tent post is safe, or maybe it's unsafe, maybe it's going to fail, right? So we need to analyze the system, but we cannot analyze the system with these three forces, F1, F2, and F3, right? How many analysis will you do? First with F1, then with F2, then with F3, then combine all those. I mean, that's a big work. That's a lot of work, right? So why don't we combine all these three forces, get one resultant force, and then do the analysis with that resultant force and see whether it's the tent post or the hook is safe or it's failing, right? So that's why we need to do this method. We need to utilize this method to find out the resultant force. Okay, all right, so we need to find the magnitude and angle of the resultant force. Let's talk about the steps. What steps are we going to follow for this problem? Okay. Step 1, resolve all the forces into their x and y components. Since we are dealing with x and y 2D system, so we have only x and y components, right? So life is good, life is easier since we are in 2D system, so we don't have to talk about the z components, right, or the third dimension. So that's it, that's simple, right? So we resolve the forces, all the three forces, F1, F2, and F3, into their x and y components. Next, we need to add the respective x and y components to get the resultant vector, right? So we do that to get the resultant vector, and then in next step, we find the magnitude and angle of the resultant vector. Okay. All right. So that's how we are going to deal with this. Now, this is the same system which was given. Now, let's talk about them one by one. Okay. So let's say this is your X, this is your Y. Now, F1 is along Y-axis, right? So this is the origin. Okay. So what that tells us, F1 is in the direction of Y-axis. So it shows us that it doesn't have any X component, right? So we can say F1X equals 0 and F1Y equals F1, right? So how do we write that in Cartesian form? We write it in this fashion. F1 equals 0I plus 300J. And always write the units, newtons, right? Because all the forces are in newtons, right? So that's why we have the unit of newtons here with F1. Okay, so 0I means 0 because F1X is 0 and 300 times J. So 300 is the magnitude and J gives the direction of Y-axis. All right, so that is your F1 resolved into two components. Now let's talk about F2. Again, we have X-axis, we have Y-axis, right? This is your F2. Okay, now we resolve this into two components. Okay, so let's say this is your F2X and this is your F2Y. All right, and this is 45 degrees. So F2X, we know that F2X is F2 times cosine of 45 and F2Y is F2 times sine of 45. Okay, now how do we write this? F2 equals F2 times cosine of 45 times I, which is the X component, and F2 times sine of 45 times J, which is the Y component, right? So that's how we resolve this F2 into X and Y components, and just use your calculators and you'll get to this. So this is the resolution of F2 into two components, negative. Now again, if you remember what we did, so now F2X is in negative X direction, right? This is negative X direction. So that's why we have this negative sign here. All right. And F2Y is in this positive Y direction, right? So that's why we have a positive sign here. Okay. And that's why we have a negative here and a positive here. All right. So that's how we resolve this F2 into two components. Now let's talk about F3. Okay. Again, this is your X and Y axis. This is X axis. This is Y axis. Okay. And F3 is somewhere here. All right. This is your F3. Okay. So this is your F3X, and this is your F3Y. All right. And the triangle ratio is given 3, 4, 5. So we'll use that to find out F3X and F3Y. Okay. So F3X would be 3 by 5 times F3, right? And F3Y would be 4 by 5 times F3, right? So this is your F3X, 3 by 5 times 600 times I. And what is your F3y, that will be 4 by 5 times 600 times J, newtons, right? Always, don't forget newtons, don't forget the units. Always remember, units need to be there, okay? Otherwise, you'll lose points. Okay, and if you do this math, you'll get this equation for F3. So 360I is the X component and 480J is the Y component of F3. Okay, and overall 360I plus 480J Newton is the vector F3. All right, so after we are done with this, let's move forward. Now sum up all the I and J components or X and Y components respectively, right? So here we add up all the I components or X components. Here we add up all the Y components or J components, right? So just add up and you get here. So this is your FR, right? 41.8 times I plus 1098 times J newtons. So this is your FR, resultant vector. Now, next we need to find the magnitude and direction of this resultant vector FR. So let's do that. We already know, okay, just show it graphically. So this is your x-axis, this is your y-axis, this is your FR, right? This is your FR. Okay, so this is the angle which it makes with the x-axis, and it has two components, fx and fy, frx and fry. So this is your frx, this is your fry, right? So just use that here in this equation, right? So FR equals 41.8 squared plus 1098 squared whole square root, right? And you get 1099 newtons. So 1099 newtons as your resultant force vector, FR. Okay, so this is your resultant force vector with the addition of those three vectors. And now, next thing is to find the direction, right? The angle of this resultant vector, FR. How do you find that? Find that in this fashion. Let's say the direction or the angle which it makes with the x-axis. Let's say that this is phi. So phi equals tan inverse 1098 or FRY divided by FRX, which is 41.8. So you get 87.8 degrees, right? So this is phi is 87.8 degrees. So that's how we are done with this problem, finding out the x and y components of all the given vectors, then adding the I and j components, then finding the resultant vector FR, and then finding the magnitude and direction of that resultant force vector FR. Okay. All right. So I hope you got something out of that example which we did. Now let's do another example for the same, right? So we have this system, we have this pipe which is attached with this wall, and there's a force of 30 pounds which is acting on this edge of the pipe, right, at this point. Okay, and this is the force, 30 pound force acting on this pipe in some direction, right, at an angle of 30 degrees from the u-axis. Now we were talking about x and y axis, but if you remember during the lecture we talked about u and v axis. Sometimes you have these kind of systems where you have some other types of axes which are not perpendicular to each other, right? So let's say in this case you have this u and v axis, right? So what do we need to do? We need to resolve the force into components along the u-axis and v-axis and determine the magnitude of each of these components. Okay, so we already saw during the lecture how we do this, right? So let's see what are the steps. construct lines parallel to the u and v axis and form a parallelogram, right? We saw earlier during the lecture how we do that, right? Then next step, resolve the forces into their u and v components, okay? Then find the magnitude of the components from the law of sines, right? So we can use geometry, trigonometry to make use of the laws and find the unknowns. Okay. All right. So let's see how we do that. Okay. So draw parallel lines to u and v axis. How we do that? So here we have the 30 pounds force, which is, let's say, vector F. This is your force vector F. Now, again, from the tip of the vector F, draw the lines for the parallel to vector u and vector v, right? So you draw this line and you draw this line parallel to u and v axis, right? So you reach here and you reach here. All right. So this is your parallelogram, right? Now from this point to this point to this, right? And this is your vector F, right? And this guy is your v component, and this guy is your u component, F sub u, right? Okay. Resolve the forces into u and v components. We already did that, F sub u and F sub v. Now, redraw the top portion of the parallelogram, right? So the top portion where we have this F sub u, on the left side we have F sub v, and on the right side we have the vector F, right? So we take that triangle or the top portion of the parallelogram to illustrate a triangular head to tail addition of the components, right? So we know that this is the triangle method or parallelogram method. They are almost one and the same thing, right? So we can show that here. We know the angles. So this is 30 degrees, this is 45 degrees, this is 105 degrees. So we know these angles, right? So now, how do we solve for F sub u and F sub v, right? So we can use, as I said earlier, we can use the knowledge from our geometry or trigonometry to solve such problems, right? So let's use law of sines here, or sine law, right? So what is sine law? Let's say there's a triangle with these sides A, B, and C with their opposite angles C, B, and small a, right? So if you have such a triangle, then the sine law says this: A over sine A equals B over sine B equals C over sine C, right? So we can use this knowledge here in our triangle, right? So this is F sub u, this is F sub v. We know the angles, right? So we can use this law of sines in this fashion. 30 over sine 105 degrees equals F sub u divided by sine of 45 degrees equals F sub v divided by sine of 30 degrees, right? Okay, so from this, we can find out F sub u, which will be 30 divided by sine of 105 degrees times sine of 45 degrees. So we'll get 22 pounds. So this is your F sub u, and also F sub v, 30 times sine of 30 divided by sine of 105 degrees. So you get 15.5 pounds, this guy, which is your F sub v, right? So that's how you can resolve this force vector F into its two components along the two axes, u and v axis, right? So we did this method and we found F sub u and F sub v, which are the u component and v component of this force vector F. Okay, so this was another problem which we did in this topic. Now we'll go to the next topic.